For a system consisting of a large number of point particles, the gravitational potential is the linear summation of the contributions from the gravitational potentials of each of the point particles in the system. This result directly leads us to a procedure for calculating the gravitational potential for a system consisting of a distribution of mass. For example, let's calculate the gravitational potential of a uniformly dense rigid rod a distance d away from one end of the rod. We can consider this rod to be a combination of infinitesimal bits of mass that we model as point particles. The mass of each of these point particles is denoted by dm. The infinitesimal gravitational potential of each point particle is found using the equation for the gravitational potential of a point particle. The total gravitational potential of the system is the sum of the gravitational potentials of each of the point particles in the system, and in the limit that these particles are infinitesimally small, this summation becomes an integral. The smallest value for the variable r in this equation, the closest any point particle can be to the position P, is d. Similarly, the largest value for r is d plus L. The gravitational potential of the rigid rod at the position P is thus defined by this integral. However, we have a problem completing the calculation since dm is a function of r. In other words, each infinitesimal bit of mass is associated with a different value of r. In order to complete this calculation, we must relate dm to r. This is accomplished by realizing that each infinitesimal bit of mass dm corresponds to an infinitesimal bit of length of the rod. Let's denote this length by dr. The variables dm and dr are related by the mass density of the rod. Let's denote the mass density by the variable lambda. Substitution of this relationship allows us to simplify our integral to one that depends upon the variable r only. Furthermore, since the rod is uniformly dense, we know that the density of the rod is constant at every point in the rod. Thus, lambda is a constant for the integral. Completing the integral gives us an expression for the gravitational potential of the rod in terms of the natural log of the variables d and L. This expression can be further simplified by substituting the value for the mass density. Since the rod is uniformly dense, the mass density is simply the total mass of the rod divided by the length of the rod. We now have our final expression for the gravitational potential of this system at the position P. For our next example, let's calculate the gravitational potential of a uniformly dense square at the position P shown in the figure. We perform this calculation by summing the contributions to the gravitational potential from infinitesimally small bits of mass in the square. As for the uniformly dense rigid rod, we could use point particles for these infinitesimal bits of mass. Since we are now dealing with a two-dimensional object, rather than a one-dimensional rigid rod, each point particle would be a rectangle with an infinitesimal area equal to the product of the lengths of the sides of the rectangle. In this case, this infinitesimal bit of area would be the product of dx and dy. The corresponding infinitesimal bit of mass, denoted by dm, would be the product of this infinitesimal area and the surface mass density of the square. We can use the variable sigma to denote this density. However, we see that we would then have to perform a double integral, one along both the x and y axes of our coordinate system, in order to calculate the gravitational potential. This is expected, of course, since we are dealing with a two-dimensional object. Alternatively, we can use a previously calculated solution to simplify our calculation for this system. Namely, rather than using point particles as the infinitesimal bits of mass in the square, we could also use infinitesimally thin rods to constitute the square. This approach takes advantage of the fact that we already have calculated the equation for the gravitational potential of a rigid rod. If these rods are infinitesimally thin and contain a mass dm, their infinitesimal gravitational potential would be given by this equation. In this equation, the variable dm denotes the mass of the rod, the variable L is the length of the rod, and the variable y is the distance from each rod to the position P where the gravitational potential of the system is measured. As discussed before, we can express the infinitesimal bit of mass dm as the product of the surface mass density and the infinitesimal bit of area of the rod. This infinitesimal bit of area is simply the product of the length of the rod and the height of the rod, denoted by dy. We can determine the gravitational potential of the square by summing the contributions from each rod. If these rods are infinitesimally small, this summation becomes an integral. Furthermore, we see that the limits of the variable y are d and d plus L. In other words, the closest any rod in the square can be to the position P is d, and the farthest any rod in the square can be to the position P is d plus L. If the square is uniformly dense, the mass density of the square is constant and can be taken outside the integral. The final calculation is a bit cumbersome to present here, but we can further simplify our expression by substituting the equation for the mass density of the square.